Good morning. This is Steve Hudson. I'm the Vice President of Hardware Engineering with Powermetrix, and thank you for joining us today. Our topic today is going to be effects on power quality on metering. Before we get started, I just want to let everyone know this is the newest presentation in our COVID-19 quarantine webinar series. We've been doing this for 12 weeks now, believe it or not, so going on the third month. Just want to let you know, this week we're also going to have a metering Q&A forum on Thursday, so be sure to tune in. I have Chris Mullins, John Jones, and myself answering your questions. So if you have a question that you would like to answer, please send that in to us today. Also want to mention, during this time, we're doing an intro on our newest system, which is our Powermetrix training bench. This is a great bench that has a variety of meter forms on it that's very useful. It actually has a load box. It can be used to simulate different air conditions, and we're offering it right now at 30% off list price until the end of the month. So please take advantage of that. Click on the Learn More button if you'd like to get more information. We think this is the new way to learn. Obviously, the coronavirus has caused us to change a lot of the way that we do business. So we'd also like to invite you, if you'd like to see a simulated product demo of either the PowerMaster series or perhaps a particular meter form, please contact us. Let us know. We can also offer demonstrations of our new training bench. This is the second or third class. This is third class. Third class in the series of 4. If you all have been attending last week and then this week, you will receive a certificate of completion. We'll send that out to you via email, so please tune in this Thursday as well for the last of our series of 4. Video setup, if you'd like to maximize this to full screen, there's a little button in the lower right-hand corner of your screen. It's got 2 opposing arrows. Click on that to blow us up to full screen to see things in more detail. Also, if you're having any sort of audio or visual issues, there's an HD button in the lower right-hand corner. You can click on that and adjust your screen resolution, which should help prevent any issues with audio or video lagging. So with all that being said, let's go ahead and jump into the focus of our presentation today. First big question, of course, is what is power quality? What is power quality, and really how does that affect you, both as a utility and as a customer? What is a power analyzer? How does that help you improve power quality? What are some examples of power quality issues that we see nowadays? And then ultimately, that you as a meterman, the real question that you as a meterman care about is, how does power quality affect metering? So with that being said, let's just jump right into it. The big question is, what is power quality? Well, power quality is a term that's a little subjective, really depending on your point of view. In this presentation, we're really going to talk about 2 different points of view, the customer, i.e. the utility customer, and then the utility's point of view. So if we start out with the utility customer, their view of power quality is really based upon what they observe. Some examples that they might have would be flickering lights. You know, if you're having a voltage fluctuation and the lights are flickering, that happens a lot. The customer is going to call you up and say, hey, I've got something going on with that. Can you guys come out and take a look at my house? Equipment reset. If you've got a UPS on your PC, for example, and you're having some dropouts, some sags in your voltage, that might cause the UPS to reset and beep quite a bit, which would also result in the customer probably calling you or just trying to understand what's going on there. Tripping of breakers. If you're having surges that could cause that, that obviously is something else the customer's going to have a lot of trouble with. They have to dig out the flashlight and go find the fuse box to get things put back into service. And so if that happens on a consistent basis, they're going to be aggravated by that. Something you might see in an industrial setting would be motors or transformers running hot. A lot of times that's caused by harmonics. We're going to talk about that quite a bit today. And then finally, lightning or other weather-related issues. Those are very intermittent problems, but nonetheless you get a lot of energy during a lightning surge, and so that can cause a lot of big problems. So if we switch gears and we say, okay, we're going to look at this from the utility's point of view, what really is that definition of power quality from the utility's point of view? We define it as a deviation from a pure sinusoidal voltage supply at a frequency of 60 hertz. In an ideal world, you know, the utility should be putting out a perfect sine wave that has no harmonics, no distortions of any kind, at a perfect frequency of 60 hertz. Now, we all know in the real world, you never see anything like that. There's always going to be some sort of perturbation or variation that will cause issues, and that's sort of what we're going to focus on today. But to just go into the subsets of things that we see in power quality, we're going to talk about sags, dips, and swells, which is just really a variation in the voltage of your system. Transient voltages, which are very short momentary problems in your voltage system. Harmonics, we'll talk about that quite a bit because a lot of modern loads have harmonics, so we'll talk about what is a harmonic and how does that affect you. Voltage regulation, and then finally frequency variations. I'm going to ask the second question, which is, what is a power analyzer? A power analyzer is a device that's used to measure components, the following components of power, with the ultimate intent of trying to figure out how to analyze, detect, and help solve power quality issues. The power analyzer is a box that really starts out sort of as a fancy multimeter, which you can, of course, detect voltage and current. Being that this is an AC system, it also has to measure phase. Phase, of course, is the time difference between the voltage waveform and the current waveform. It has a lot to do with power factor. So from the phase, it can derive the power factor. It also measures the frequency of the system. So if you're over in Europe, of course, that would be 50 hertz. Here in the United States, that would be 60 hertz. What we can see that if we get even a slight bit off of that 60 hertz, that can cause all sorts of problems. And then finally, harmonics. Harmonics being multiples of the fundamental frequency of 60 hertz. Second harmonic would be 120, third harmonic would be 180. So we'll talk about how those are generated, how those affect the system, and what we can do about it. The power analyzer is designed such that it can take data over long periods of time, because a lot of times power quality issues may not be easily detected just by one trip. A lot of power quality issues may be very momentary, very intermittent, meaning that you really have to look at a long set of data over the course of hours or days to be able to catch it. Sometimes you're looking for a trend in terms of voltages going up and down, and so you're trying to correlate those trends with equipment being turned on and off. And so really the power analyzer has to have the ability to be able to monitor all those things we just talked about over a long period of time to be able to do that. A lot of times that can be done with a PC. For example, you can take a laptop out with a power analyzer module that plugs in. More modern power analyzers are self-contained, meaning that they have basically memory inside of them, and so they can be taken out to remote sites and plugged in and record that data for long periods of time. It used to be that you'd have to go out and install it and record that data for a long period of time and then go back out to the site and take it out. Now that we live in a wireless world, a lot of power analyzers now have wireless connectivity, and so it can basically stream that data live to you, or it can do a big download, say, once a day to do that. So that makes it a lot easier in terms of you just have to install it and be able to get the data out to look at it. Once again, the ultimate intent of all this is that we are trying to determine power quality issues, a lot of times trying to find those problems that we mentioned before and take care of it. A lot of time on the customer side, they will use a power analyzer for reducing energy usage. Once again, if they're doing trends, looking at their watt hours over the course of a day, they might want to see how can I go and best maximize my energy usage to help reduce my energy bill. So let's go ahead and talk about the subset of different power quality issues that we see as both a customer and a utility. First one we're going to look at is sags and swells. And so a sag and a swell is defined as a deviation from the normal RMS voltage, which may last from half a cycle to several seconds. When I say deviation, a sag is actually going to be a reduction in voltage. If we're talking about normal residential service, say 120 volts, that may go down quite a bit below that, or a swell, meaning that we have a voltage that goes up above that. We mentioned that can last anywhere from half a cycle. Now mind you, half a cycle meaning half of a 60 hertz cycle. 60 hertz cycle is equivalent to about 16 milliseconds. That's 16 thousandths of a second. So half a cycle would be roughly 8 milliseconds. So we're not talking about really a terribly long amount of time. In the world of modern electronics, that's a long time, but in human time, that's a very short time. Half a cycle to several seconds. Sags and swells are some of the most common power quality issues we see today. It's very noticeable to customers because the voltage, of course, has a direct effect on your equipment. Lights, of course, good old-fashioned incandescent lights really require that the light output is going to be proportional to the voltage. So if you still are using incandescent lights and you see a large sag or swell, that will result in the lights notably either dimming or getting brighter. My particular utility actually typically tends to run high. I was actually measuring the voltage the other day and I was recording upwards of about 128 volts coming out of my wall outlet. Now that's pretty darn high. Most electrical equipment, of course, is designed to accommodate a wide range of that, and we'll actually talk about what those ranges are here in just a minute. But I will say this, a lot of times most equipment is more forgiving of a sag than a swell, meaning that if I have a dip in my voltage, a lot of equipment will ride through that. However, if I get a swell, I will say I've gone through a lot of light bulbs with my particular utility just by the fact that they run a little bit higher than the typical voltage on the utility. The cause of a sagging swell is typically due to infrastructure sizing and a load issue. Transformers are unregulated to some degree, and so as such, as you switch in large loads, that will cause a sag or swell. If another load comes off, basically removing that load will cause the voltage to jump up. And so what you'll see is that it will cause that really depending on the load being applied to the system. For the meterman, the important thing to note is that sags and swells typically are not an issue in terms of metering accuracy. That's because the meters are designed to accommodate a wide range of voltages. And so even if it's designed to be nominally a 120 volt meter, the ANSI C12 standard, which dictates how a meter is designed and built, basically will accommodate anywhere from half the nameplate voltage to twice the nameplate voltage and still not damage the meter or really affect the metering accuracy. If we look at a graphical representation of this, what we've got here is a sag. And so if you look at our time base, this is just over the course of a few seconds. And so the dip is going nominally from 120 volts all the way down to 112 volts. So you had about an 8 volt dip there. And the time base, that lasted much less than just 1 second, probably a few tens of seconds. That short of a perturbation normally would not be noticed unless you had a really sensitive piece of equipment. In terms of the meter's averaging it. And so as such, it's just going to see that blip and move right on without even thinking about it. If you think about the meter this way, how often do we go out and read our meters? Conventional sense, it's usually once a month, every 30 days. And so if I've got a perturbation that's lasting only a few tenths of a second, the meter's going to average that, and there's not really going to be an issue at all in your bill. Here's another example that was out at I think a milling plant. What you see here is that you've got a periodic waveform issue going on, and so we'll have a spike. You've got the voltage on the top, and you have the current on the bottom. And so periodically we will get a current spike, and that spike in current may be where a piece of equipment is going and switching into the system, or that it's perhaps a switching power supply that's causing that to pull a large transient. And what you'll note is that the voltage will dip momentarily while there's that large surge in current. So once again, that's a regulation issue. Once again, for the meter, that's not a problem. It's averaging over a long period of time. And so as such, these sort of even periodic kind of perturbations are not going to cause a problem for your metering. Moving on to the second issue, transient voltages. Transient voltages are very short deviations from the normal sinusoidal voltage, normally referred to as spikes. Probably the most common example of that would be lightning. Lightning, of course, is a very intermittent phenomenon. It's not happening on a regular basis. And so as such, the system is designed to accommodate that. Most meters, I shouldn't say most, all meters are really designed to stand up to lightning events. There's a huge amount of energy that goes into that. I can say that since Powermetrix has designed Category 4 safety equipment, we actually design our equipment to withstand lightning strikes, and so the simulation of that is a 12,000 volt pulse for a microsecond. A microsecond is 1/1,000,000th of a second, so it's a very short event, but you've got obviously a lot of energy packed into that. Meters, once again, are designed to withstand that. It's got protection equipment that's designed to accommodate that lightning strike coming in and then shunting that energy. Those protection devices, of course, do have a lifetime, and so if you live out in the Midwest, say where you have a lot of lightning, it may be required that you have to go and change your meters out a little bit more often than not. But the meter itself is designed to ride through that, and as such, it shouldn't really be a problem in terms of the accuracy of the meter. Like I said, it may cause more damage, but it really won't cause a problem in terms of the accuracy of the meter. Another example of transient voltage will also be capacitive switching. So if you have cap banks that are being switched in and out of the system, sometimes you'll get a large spike when you do that. Here we have another visual example showing once again the voltage and the current of a system. And so what we see is that the voltage is going along nice and clean until you get this huge spike in current, and then you see a large distortion in the voltage waveform. But you'll note that basically the voltage has recovered not even one cycle into the future. And so once again, that shows there's a lot of resiliency in the distribution system to recover from these sort of events. I mentioned earlier voltage regulation. Once again, we're talking about long-term variations in voltage over the course of seconds, hours, minutes, hours. ANSI C12 defines the deviation that can happen from nominal for both a service range and a utility range. A service range is basically looking at the service entrance, so that would basically be where the meter is being hooked up to the system. Range A is normal conditions, and it has two definitions: for less than 600 volt system or greater than 600 volts. So for less than 600 volts, you have a plus or minus 5% deviation in surface entrance. So you can have a little bit above that or a little bit below that. Most equipment is designed to accommodate that, and so as such, if you as a utility go in and can maintain that level, then most of the time the customer isn't going to see a problem. For greater than 600 volts, you're giving a plus 5% on the high end and minus 2.5% on the low end, so it's a little bit tighter just by the fact that the equipment probably doesn't want to deal with a lot less voltage than that. Range B is defined as a short duration or unusual condition. So that would be more like the sag or swell or transient conditions that we mentioned earlier. And so what you see is that you have a little bit more leeway, goes from plus 5% to plus 5.8%. On the low side goes from minus 5% down to minus 8.3%. And so they expect a little bit more of a sag if you have a short-term issue. Once again, this is not a metering accuracy issue. The meter is designed to average it over the course of a long period of time, and so voltage regulation is really not going to affect the meter because it's designed to work over a wide range of voltages, and it's just going to average that out. If we talk about the utilization range, utilization is basically where the customers plug into the wall, and so what you'll see there is, once again, you're giving a little bit more leeway from the service entrance. For less than 600 volts, you can go down to as much as minus 10% or as much as plus 4.2%. So once again, the equipment is designed to those sort of ranges. It will be much more forgiving if we have a sag as opposed to a swell, just because that's the way that it's specified, that's the way it's going to be designed. Once again, the short durations, we can have up to minus 13% or plus 5.8%. Yet once again, metering actually is not an issue because the meter will average that and there won't be a problem. Bottom line is that if we provide service that meets the service range requirements, in other words, where it's coming into the meter, coming into the customer's building, the customer utilization range requirement should be met if they've wired up their house or company properly. Here's a picture of voltage variation over the course of a day. And so what you'll see is that if you come in early in the morning, this thing's typically riding up close to 120 volts. This is probably 8 a.m. when everybody comes into the building, everybody turns on the lights, turns on their computers, HVAC system kicks in. You'll notice that there's a large drop. And so that gradually sort of builds up over the course of the day and then just goes again. So you have a very cyclic phenomena. This particular system is only deviating between about 120 volts and 114 volts. So that's still well within the utilization range called out in the earlier slide. So that's probably not going to be a problem. Talking about frequency stability. Frequency in the United States, we're very blessed to have a very stable system. Typically, our system is 60 hertz, and it will wander off of that a few millihertz over the course of a day. Back in the olden days, of course, analog clocks were actually derived their time base off of that, and so what that means is that the clock may go a little bit faster during the course of the day and might slow down a little bit, but over the average, it was pretty close to perfect on 60 hertz, and so as such, the clocks really didn't lose time. If we look at a lot of the data here in the Western world, what we'll see is normal deviation should be no more than plus or minus 15 millihertz. That's 15 thousandths of a hertz. So once again, we have very good regulation on our frequency. A sudden change is defined as up to plus or minus 1/10 of a hertz. And that may occur several times a month, just depending on the situation. Once again, most utility equipment is designed, or most equipment in general is designed to accommodate that. It shouldn't be a problem. Every now and then you'll get a major breakup, which is defined as plus or minus 3/10 of a hertz, which should be once every few years. Now that doesn't sound like a lot, but that can lead to catastrophic issues, including brownouts and blackouts. The University of Tennessee actually has a specialty program designed on monitoring the health of the system, including frequency monitor. There's a lady there that actually is known as as sort of the matroness of phase monitoring units that go out and monitor the reliability and the accuracy of the 60 hertz over the United States. They actually have some very interesting demonstrations of how a brownout or a blackout situation can spread from a very centralized point across the map. And so if you have a chance, go out and look at that. The name of the program is called Current, C-U-R-E-N-T, at the University of Tennessee. Once again, doing some really neat research to show how changes in frequency can cause breakdown over time. This particular issue actually can cause metering issues, especially for our measurements, simply by the fact that a lot of meters were designed based around a 60 hertz clock coming into the system. There's been a lot of improvement in that over the last few years. We'll talk about harmonics here in a little bit. That pertains a little bit to this. But historically speaking, this could cause a lot of problems because the meters were designed really to expect a pure 60 hertz signal, and so any deviation off that frequency could cause the electronics to misbehave and cause metering issues. Moving on to the next issue, harmonics. Harmonics is defined as a repetitive contamination of voltage and current waveform. And if we break that down a little bit further, the first word there that's really important is repetitive, meaning that a harmonic waveform is something that happens over and over and over again, pretty much every cycle or every few cycles. That's to be distinguished from a sag or a swell, which may be, once again, based on load and vary over the course of a day. It's very different from a transient kind of thing, like a lightning strike, which may happen very intermittently. Harmonics really are mostly generated by nonlinear loads. A nonlinear load basically means that if I take a load and I put it on a sinusoidal voltage source, I'm going to end up getting a response out of my system that no longer looks sinusoidal. It'll be periodic, it'll have the same waveform over and over and over again, but basically it'll no longer have a sine wave output. If I think about the current being a function of the load, if I have a linear load and I apply a linear load to a voltage, to a sinusoidal voltage, I'll expect to get a sinusoidal current out of it. If I go and apply a nonlinear load to a sinusoidal voltage, I'll get a waveform out that looks nothing at all like a sine wave. And we'll see a couple examples here in just a second. Harmonics can cause a variety of infrastructural problems. In particular, it can generate system losses, and it can also generate excessive heat in the equipment. Transformers in particular don't like harmonics. Most distribution transformers were designed, of course, to transmit 60 hertz loads, and so if we start to have higher and higher frequency harmonics, that's going to end up generating extra heat in those transformer coils. Once again, most electronics don't like to run hot. It will reduce the overall lifetime of the equipment, and so as such, you may have to replace equipment more often because of that. Harmonics can also result in metering errors, in particular VA and VAR error measurements. There's not a standard right now for those, and so as such, depending on how that is being calculated, it can potentially cause some issues in that. If we talk about harmonics in a little more detail, the way that we measure harmonics in modern days is that we use something called Fourier analysis. Fourier was a French mathematician that a couple hundred years ago basically went and figured out that any periodic waveform can be broken down into a bunch of sine waves. And so he used what's now known as Fourier notation or Fourier analysis to be able to analyze that periodic waveform and do that. And so there's the formula given for that, Fourier notation. If we take a more practical example of that, let's say we've got a 60 hertz waveform, which is the dark blue waveform on your screen. If we go and we take a 300 hertz harmonic, 300 hertz is the fifth harmonics, 5 times 60 is 300, and we sum those together, what you end up with is this light blue harmonic. And so this would be something that has a fair amount of harmonic energy on it. If we take yet another example, we take a square wave and start to break that down. Square wave might be typically the output that you get from a cheap AC inverter. And so if you go down to Walmart and you buy one of these inverters that you can plug into the 12-volt cigarette lighter adapter of your car, and then you looked at the waveform, that might be what you see. And so what you realize is this is in fact 120 hertz, but it's a 120 hertz square wave. Square waves are made up, an ideal square wave is made up of the infinite number of odd harmonics of the given waveform. So that'd be the third, the fifth, the seventh, the ninth, the odd harmonics. And so you see a lot of these odd harmonics are adding up to give you this square waveform, albeit with some more harmonic noise riding on top of it. I will say right now, if you really care about your equipment, do not buy a cheap AC inverter. I've lost several computer power supplies due to that. What you want to look for is a true sine wave inverter. And so what that means is that they're going to put a filter into the back end of that thing to get rid of all those odd harmonics and give you a waveform that looks more sinusoidal. That'll make your equipment last a lot longer. Got a question?
Yep.
Okay, Chris got a question.
Got a question from Mike. What type of metering is more impacted by harmonics? Hall effect or CT sensing?
Good question. Hall effect sensors, if I remember correctly, are mainly working off magnetic sensing. Now, what was the other half of that? The CT?
Hall effect or CT sensing?
I'll be honest with you, I don't really know the answer to that. My guess is that it may be Hall effect. Really depends on the magnetic field that's being generated off of that. What we probably ought to do is we ought to research that and get back to that. So Mike, if you can send us your email, let's research that and we get back to you on that. It's a good question though, thank you. Moving on with harmonics. Where do the harmonics come from? Harmonics once again come from nonlinear loads at a customer's site. That could be a variety of different things. It could be something as simple as the lighting. Here in a moment we're going to look at different kinds of lighting and what sort of harmonics are being generated from that. It could be something like, say, an arc welder, something that draws a large transient of current on a momentary basis, on a periodic basis at very small moments in time. One of the problems with harmonics is that it sometimes can couple due to the loads to different sites sharing distribution systems. In other words, if you have one customer that has a really bad load that generates really bad harmonics, sometimes that can actually cause those harmonics to be transmitted back to other customers. And so as such, that's really where you as a utility may have to go out to the customer and say, hey, Mr. Customer, we're going to have to do some sort of power quality analysis to figure out what your problem is, either that or put it back on the customer, have them do it. A lot of times that may end up the customer may have to install a filter or something to be able to prevent that from getting back out into the system and affecting other people. If we look at past harmonic sources, in other words, over the last 100 years, what sort of things cause harmonics? Most notably, transformers. A transformer, of course, is designed to accommodate a certain amount of power. If you exceed the power rating on a transformer, it will go into saturation, meaning that basically I can't get any more power out of this transformer. A lot of times it will end up truncating the sine wave, and so it will go from a nice sinusoidal waveform to looking more like a square waveform. And as we saw earlier, that can add quite a bit of harmonic energy. And so the output level could be anywhere from 1 to 85%. Mentioned arc furnaces, arc welders, things that are drawing large transients of current will generate a large amount of harmonic energy. It can generate voltage harmonics on the 5th and 7th anywhere from 2.5 to 8%. Some other examples are line commuted converters, static VAR compensators, saturable reactors. Once again, that's older equipment that can cause a variety of different harmonics, anywhere from a few percent to several tens of percent. If we talk about new harmonic sources, these are things that we see a lot more nowadays. What we find is lighting in particular can cause a lot of harmonic energy, and we're going to give you some very specific examples. Fluorescent lighting, for example, can generate up beyond 400% of harmonic energy. And so as such, that's a big problem. One thing I didn't mention was how do we measure that? The normal units of harmonic energy are THD, total harmonic distortion. And really what that number is it's a ratio of harmonic energy to fundamental energy. In other words, fundamental would be 60 hertz energy, which is doing most of the useful work, and then the harmonic energy, once again, is not doing useful work. It's typically being burned up as that. And so, as such, I can have a THD level of greater than 100%, meaning that more harmonic energy is being put into my load than fundamental energy. And a lot of times, as I said before, that's being given up as heat, cause your equipment to overheat and cause all sorts of failures. All right, so here's one of my favorite parts of this presentation. Once upon a time, we actually did a comparative study of 3 different light bulbs, just to show the harmonic effects that you get from a modern lighting source. And so what we did was we took 3 bulbs. We took an incandescent bulb, a compact fluorescent bulb, and an LED bulb. We chose the bulbs so that they were equivalent in terms of the light output, because normally that's what the customer cares about. The customer cares about, how much light am I going to get out. What you're going to see is that, yeah, you can actually save some money on your power bill from these different light sources, but it does come at a price. And so if we start out with the 60-watt incandescent light bulb, what we have here is that we have the voltage and the current waveform. The voltage is the skinny red waveform, and the current is the dark red waveform. An incandescent bulb basically is a filament. It's a resistor. 100 years ago, of course, good old Thomas Alva Edison figured out that he could go and stick a tungsten element in there and create a lot of light, and it would last a fair amount of time. And so up until recently, that's really been the standard for light bulbs. And being a resistor, what that means is that it's going to have a power factor very near to unity. If we looked at our active power, this particular bulb, this is called a green 60-watt bulb. And so it outputs the same light output as a 60-watt bulb, but it only consumes 41 watts. Not entirely sure how they did that. If somebody knows, please let me know, because I've had that question asked, but still haven't got a good answer on that. Probably different material, different gas inside the bulb, but nonetheless, the thing that we care about is it still really doesn't generate a lot of harmonic energy. 41 watts, less than 1 VAR of reactive power, so nice clean power. Power factor is very close to unity. Mentioned earlier the THD level. Current THD is 1.5%, so once again, that's a very low amount of harmonic energy. If we go to the next example, compact fluorescent light bulb. Once again, this is 60-watt equivalent, so it's outputting about the same amount of light, which ultimately is what the customer cares about. But what we notice is that we've gone from 40 watts on the incandescent bulb down to now 14 watts. So basically 1/3 of the active power being consumed. So, for the customer, that's a great savings. He's being billed on watt hours, and so, if I can go and replace all the bulbs and basically get the same amount of light out, but only consume 1/3 of the wattage, then that's going to be a great savings. Now, the flip side of that is, for the utility, guess what? It's going to generate VARs. It's going to generate reactive power simply by the fact that it's a nonlinear load, and it's going to start to exhibit both harmonics and VAR hour reactive loads. The apparent power, which of course is the vector sum of the active and the reactive power, is going to be 16 VA. And so the bottom line for the utility is that, if we go back to the incandescent, we're getting 41 watts out, apparent power is 41 VA. I've got a watt-hour meter sitting on my residential service, and so guess what? I'm capturing all of the energy being delivered to that bulb. Now on a compact fluorescent bulb, we've only got 14 watts. We're still measuring watts, but we've now got 16 VA. So what that means for the utility is, for each and every compact fluorescent light bulb out there, there are 2 additional VA that are not being measured. And so that's a loss. That's a loss to the utility. And so they're losing a little bit of money on each and every compact fluorescent bulb out there. Now the other kicker for the utility is the amount of harmonic energy being generated. So for this particular system, our THD, our current THD is 88%. So that means 88% of the energy being delivered to that load is being dissipated as harmonic energy, and most of the time that's going to be heat. I mentioned earlier about nonlinear loads not being sinusoidal. Once again, I've got a sinusoidal voltage going in, but now if we look at the current waveform, it looks like sort of a rugged mountain peak. And so this is just a surge of current being drawn on each and every half cycle of this waveform. The more jagged, the more sharp that peak is, the more harmonic energy is going to be consumed from that. If we look at the next example, which is an LED bulb. LED bulb uses even less active power. We're now down to 11 watts, and so that's only about 1/4 the energy that was being consumed by that 40-watt bulb. Reactive power, we're still generating 4 VARs for each and every bulb that we've got. Parent power is 12 VA, and so once again, there's 1 extra VA being consumed by this bulb that most likely is not being measured by that watt-hour meter on the side of your building. And so what that means is that we've got a little bit of a loss once again. The big loss, however, comes in harmonic energy. We have a current THD of 111%. And so what that means is there is more energy being dissipated as harmonic energy than fundamental energy. And once again, that's most likely going to be burned up as heat. One thing that I noticed, several years back, I switched over from incandescent bulbs to compact fluorescent bulbs. More recently, I've switched over to LED bulbs. As I pulled out some of those compact fluorescent bulbs and some of those LED bulbs, what I noticed was the base of those bulbs have gotten very yellow. In other words, they've been generating a lot of heat. The bulb itself will run cool, but the base, of course, actually has a converter in it. An LED bulb, LEDs are DC lighting sources. So what that means is you're taking that 120 volts AC signal, you're converting that to a DC voltage, and that's being provided to the LED to be able to light that bulb. That AC to DC conversion is via what's called a switching power supply. Switching power supplies are probably one of the worst nonlinear loads that we have out on systems today. And so as such, it's generating, in this particular example, 111% of the energy is being generated as harmonics, and so that's a lot of heat. It's funny because on the side of the box, LED bulbs in particular are supposedly rated to last many, many, many years, which is one of the big advantages that's being proposed. I think the reality of it is that they don't last nearly as long simply by the fact that that heat, once again, will cause the electronics to run hot and will burn it out sooner rather than later. And so you still may get, a couple of hours of couple of years of use out of an LED bulb, but keep in mind it's still going to run hot because of that harmonic energy. The last example we're going to look at is a laptop computer power supply. This is actually the one I've got plugged in my computer right now, and so what you'll see is the active power being consumed here is 35 watts. So it's a fairly low power supply. However, if you look at the reactive power, it's consuming 6 VAR, and so parent power vector sum of those two is 37. So once again, there's 2 VA being consumed, which the utility is not being paid for, simply by the fact that we're probably doing watt-hour metering and not VA hour metering. Current THD is even worse than the LED bulb that we looked at earlier. Almost 150% of the energy, 1.5 times the energy being consumed over the fundamental energy being put into that system. Once again, if we look at the waveform, the current waveform, you got a really sharp peak here at every peak and trough of every sine wave. As I mentioned earlier, that's a function of load. There are supplies out there, there are light bulbs out there that have compensation for that. In Europe, as a matter of fact, they are actually required to add compensation because they knew that when they switched over from incandescent bulbs to compact fluorescent bulbs, for example, there was going to be a lot of harmonic energy. And so the European Union went and mandated that they actually had add an extra little circuit into that to try and help that. And so as such, European bulbs are going to be a lot closer in terms of the power being metered to what's actually being consumed. Pass that cost along to the customer, may cost an extra couple of cents. So from the customer's point of view, they're still getting a good deal because they're still consuming far less wattage. good deal for the utility because once again, the VA being produced is very close to the watts that's being metered. Let's talk about an alternative approach to look at harmonic theory. Harmonics can be grouped into sequences, which helped us to understand their effects. So once again, if we talk about each of the harmonics, we have the fundamental at 60 hertz, second at 120, third at 180, so on and so forth. If we look at sequencing, we have positive, negative, and 0th order harmonics. The positive happens on every fourth, so you go fundamental, fourth, seventh, etc. Negative happens second, fifth, eighth, and then on the thirds we're going to have 0. What that means in terms of reality is, if I look at a positive harmonic, let's say we've got a 3-phase system, and its rotation is ABC, and we've got that hooked up to a 3-phase meter. A positive harmonic, what that's going to do is that's actually going to try and push the motor to move a little faster. Those positive harmonics add up in such a way to induce the magnetic fields to run that motor a little faster than what it normally should be. And so that is a little bit of a problem in that the motor really wants to run at a particular frequency, and so if I'm pushing it to go faster, that may cause more friction, may cause the motor to burn up earlier. If we look at negative effects, that's going to have the opposite effect. That's, instead of making the motor run faster, it's going to make it run slower. And so it starts to pull it back, once again causing more friction, may cause that meter to burn up sooner rather than later. That motor, not meter, sorry. And then finally, 0th level. These are called triplins or thirds. These are a real big problem, simply because of the fact that all 3 phases, the returns are in sync. A lot of times, the reason that's a problem is that those currents end up going back through the ground conductor. Rather than going through the neutral, they're going through the ground, and so it can cause a meter base to burn up. One story that I heard at a meter school once, that there was a customer out in Phoenix, Arizona. It was a golf course, and they had recently switched over from using gasoline go-karts to electric go-karts. Unbeknownst to them, the battery charging system had a real problem with these 0th level harmonics. And so as such, all these harmonics summed up together, all that current was being dumped back into the ground conductor. It basically overloaded that ground conductor, caught the clubhouse on fire and burned it down, just because of the fact that they didn't realize that there was so much harmonic energy being dumped into the system. Real story. So once again, in summary, we can look at harmonics as either positive, negative, or 0. Positive can cause heating of conductors or transformers because it's trying to push that motor to run a little faster. Negative harmonics can also cause heating of conductors for the same reason but slowing it down. And 0 can return in neutral currents that can be larger than the phase currents, once again cause overheating or even fires. Harmonic and metering accuracy, there is a problem that we have right now in that we do not actually have a standard for VA or VAR hour metering. The ANSI C12 committee has been working on that for several years. There's one particular committee that's dedicated to that. Right now, getting much closer to coming up with a standard way of doing that. Something that the ANSI committee did do recently is that they did decide to go ahead and add 6 harmonic waveforms to the C12.20 standard, which is basically the standard by which all modern solid-state meters are built. And so if we go and we do, the meter manufacturers have to do something called type testing, meaning that they basically have to go through all of these different tests before a meter is released out into the real world. Those 6 harmonic waveforms were made such that to represent 6 different harmonic loads that are seen out in the real world that would need to be applied to each and every meter to guarantee that every meter would get consistent results. The reason that was a problem was that, historically speaking, you could take that same load, you could take 3 different VA hour meters, you could run on the same load and get 3 different answers, in some cases up to 50% different answers. That's an issue that has been addressed by ANSI, has been addressed by the meter manufacturers. Good news is a lot of modern meters will meter harmonic loads without any problem. But ANSI took the extra step of actually taking precautions by adding those 6 waveforms to the type test so that each and every meter do have to be qualified to that. What we're going to do is we're going to go through and look at each one of these. We're actually going to have a demo here in just a minute to actually show you how our equipment can actually generate these waveforms and show you how that affects the metering accuracy. So the first waveform we're going to look at is called a phase-fired waveform. We here at Powermetrix refer to this as the shark fin waveform for obvious reasons. It looks sort of like a shark's fin. This is the current coming out of the load. This particular load actually represents a good old-fashioned dimming circuit that you might have, say, in your dining room. They used a solid-state device basically to go and only turn it on for half a cycle. And so the net result was that, you know, you're only giving half of the waveform to the light bulb, therefore it'd only be half as bright. This has a lot of harmonic energy. Once again, if you have a very sharp edge, that sharp edge produces a lot of harmonics. And so this is probably one of the worst harmonic loads that we have, the 6 waveforms that are being defined by ANSI. This particular waveform can be defined up to the 20th harmonic is the minimum that the meter manufacturers have to test for. It could actually easily be generated all the way up to the 100th harmonic. Second waveform we're looking at is the quadriform waveform. And so what you have here, we have the waveform defined in both voltage and current. Voltage is still fairly sinusoidal. You'll see there's a little bit of lumps and bumps in the voltage. But the current waveform is a very square waveform. And once again, a square waveform, as we saw early on in this presentation, is made up of many odd harmonics. This is a switch load device, so you may have a system that's switching positive and negative, thereby generating this square wave looking current waveform. Once again, this has a lot of harmonic energy, could potentially cause some problems for meters just by the fact that, you know, it doesn't like that extra harmonics at those higher orders. Electromechanical meters, historically, of course, were designed to measure 60 hertz, the fundamental. Some other companies have done tests on those electrical mechanical meters and have found most electrical mechanical meters start to peter out about the 7th or 8th waveform. And so if I've got a waveform like the phase-fired waveform or this quadriform that have harmonics up into the 10s and 20s, solid-state meters do a really good job. Electromechanical meters, not nearly so much. They start to lose a lot of that high-end energy. Third waveform we're going to look at is one that's very popular nowadays, the peaked waveform. And so once again, you have a fairly sinusoidal voltage source, but you have a peaked current waveform. And so if we overlaid these, you'd see that the peak of this current basically causes an inflection in the voltage source. This is coming from a switch power supply. Most all equipment that you have nowadays run off of that, whether it be a PC computer, a monitor, a television set, even a refrigerator. I went out and bought a refrigerator a few years ago. It had in great big letters on the outside of the refrigerator, Energy Star compliant, direct drive motor. Rather than using a good old-fashioned AC compression motor, they put a DC motor, DC stepper motor in there. What that means is that the 120 volts going to my refrigerator had to go through an AC to DC conversion, the switching power supply, to be able to drive that DC motor, generated a tremendous amount of harmonic energy. Saved me energy because the total watts being consumed by that refrigerator went way down, but it generated a lot more harmonic energy, meaning that there were more VARs and more harmonics that the utility was paying for that were not being caught by the watt-hour meter. And so once again, that's a loss for the utility. Fourth waveform is yet another example of a switching power supply called the pulse waveform. Once again, you have a sinusoidal voltage, big current spike on each peak and trough of every sine wave. Once again, you see even more pronounced on this is the little inflection that's being caused because of that surge, that current surge. And that's each and every cycle. That will now go away until you either change the load or filter the load in some way to be able to get rid of that. Next waveform is called the multiple zero crossing current waveform. So once again, we have a perfect sinusoidal voltage. We have a current waveform that is just sort of a mess. It's got all these lumps and bumps. What you'll notice is that there's a lot of zero crossings. Now the reason that's important, of course, in the sine wave, you really only have one zero crossing. You have it where it's going from the top to the bottom, goes through that. Back in the day, a lot of meters were dependent upon that sinusoidal waveform for its fundamental clock, for its 60 hertz clock, which drove a lot of the digital electronics. And so some meters might use the voltage, some might use the current. The problem being that if I go from having a nice clean transition, meaning I'm generating a nice clean square wave at 60 hertz, if I've got this waveform that's got all these zero crossings, that's going to generate a very confused looking clock. And so as such, the digital electronics of the meter might get confused to the point that it might give a very bad answer. And that was true. There for a while we had some meters that would get very confused by that. The last waveform is basically multiple zero crossing, but that's on voltage, not current. And so as such, now I've gone from a nice clean voltage to a square wave looking voltage. I mentioned earlier that you might see that coming out of a cheap AC inverter, but the current is now sinusoidal. I'll be honest with you, I don't know of any real world waveform that would give you a really ugly square wave voltage input and a nice clean current output. I think you'd probably get more of a combination of both the current waveform and the voltage waveform. Nonetheless, the fact that you've got multiple zero crossings on your voltage, that's still going to cause some meters to get confused and give very bad results. All right, so next thing. Mentioned before, there is not a standard calculation right now for that, but the ANSI committee is working on that. We did do some experiments. A couple other manufacturers have done experiments and found, historically speaking, older meters can have up to 50% difference in their answers for the same harmonic waveform when running on VA or VAR metering. Good news is a lot of modern meters have taken that into account. There are some meters still that you can actually select the different calculation modes. There are about a dozen different ways, half a dozen different ways that you can actually calculate that. And so certain meters would allow you to program the math to be able to do that. And so if you do have a meter like that, please be aware of what mode that you're using, because you can get very different answers depending on what method that you're using to calculate VA or VAR. Last thing that we're going to talk about is some other power quality issues that we've not really touched on today. Another issue that we see nowadays is called subharmonics. Subharmonics would be harmonic energy that is actually less than the fundamental. Rather than being 60, 120, 180, it would be, say, 30 hertz or 15 hertz. These are not being addressed in any standard right now. They're not being measured by any sort of 4AA-based approach. So as such, if you have systems that are generating subharmonics, that could still be a problem for your meter or your power quality equipment. And so as such, you need to be sure to pay close attention to that. Another issue is a non-harmonic high-frequency disturbance, not being addressed by that. And once again, don't show up in any of the 4A-based approaches for doing metering right now. And the last thing is sudden load change. Sometimes if you have a really, really sharp transition in your load, that can, once again, generate some high levels of harmonics. Not being addressed in any standards, and once again, may not be caught by your 4A. Really depends on the sampling rate of the meter as to whether or not that would be caught or not. Since we spent a lot of time on harmonics, I guess one big question is, okay, fine, we know that they're out there, how do we get rid of them? The big answer is that unfortunately there is not any one-size-fit-all solution. Each and every harmonic load is a little bit different, and so as such what that means is to be able to fix the problem, you really have to go out to the site, you really have to do an analysis, and then you really have to design a solution based upon what the load is. Some examples of solutions that are out there, first of all, would be an active filter. Active filter is going to be a system that's going to actually go out and measure the harmonics and generate a mirror image. It's basically sort of counter opposing that. Those of you that use these noise reducing headsets use the same principle. Basically what it does is the headset measures the outside noise, say there's a vacuum cleaner running. It measures that, it analyzes the harmonic, and then it injects that waveform into your ears, which is a mirror of that waveform, in effect canceling it out. The active filter for an active harmonic system will actually go and do that. Once again, those are very expensive because you've got a digital, a lot of times this is done digitally, and so it'll go and do that. So it may depend on just on the level of harmonics and the frequency of the harmonics. Another way of doing that is a tuned filter, which is a filter that is basically designed for a particular pass band, maybe used to cut down. A lot of times it's going to be a low pass filter, meaning that it's going to pass the 60 hertz, but we're trying to get rid of all those higher level harmonics. Once again, very effective, but can be very expensive. If it's a passive filter in particular, it's apt to generate a lot of heat, and so as such, you're going to have some very large devices, very, very expensive, a lot of heat being generated, some of the issues that can come up with that. Another example that was given to me by a friend is something called a zigzag transformer. That's something I'm not overly familiar with, but apparently that's something that's used to reduce third level harmonics. We mentioned that issue with the charging station at the golf course. So that might be a good solution for that. Once again, there's not a one-size-fits-all solution. There are lots of folks out there that specialize in doing power quality analysis, and so they've got a lot of business just based on all the different things that you might see. Last thing I'm going to leave you with is some of the power quality standards out there. IEEE in particular has a lot of different standards based on power quality, depending on the particular issues. I recommend that you go out and look at these. IEEE.org is the website that would have these. So we've got 2 pages of those different kind of waveforms, different kind of standards. So with all that being said, stand by. We're going to show you an example of how our PowerMaster 3 series can actually generate some of these new waveforms.
As we're kind of running out of time, we only got about 5 minutes left. I went ahead and run a test so you guys can kind of see how the equipment works. But those of you who have a 3 series and you have a Model 335 load box, going over some of those sample waveforms, you can actually simulate those using the Model 335. Jared, can you go to the slide that shows the setup screen? In the PowerMaster, and Jared's going to show us a screenshot of the phantom load setup. So if you want to use some of these harmonic waveforms, there is a setup screen in there. And if you look at the column that says harmonic, you can actually enter into that field, and there's a drop-down box in that harmonic cell. 3 options there is sine, phase fire, and multiple zero crossing. The sine is meant to be a true sine wave. It's just sinusoidal. There's no harmonics applied. The phase fired is kind of what Steve was talking about, that shark fin waveform. And the other one is a zero crossing, which is an interesting waveform. I'll kind of show that. So if you can actually select that, save that setup, and run this. Now, this new standard that ANSI C12 just came out with is meant for type testing, but you can actually use these same waveforms out in the field to determine how well your meter is doing. And then, Jared, if we go to the 3 series now, the tests that I've run are complete. What I did is I ran first did a phase-fired waveform, and the meter performed very, very well. I'm actually running a test on a Landis-Gear Focus AXR, so very, very good. And all the ones that we've seen so far as solid-state meters go, they seem to perform well on these crazy waveforms with high harmonics. What we have seen is that mechanical meters do not do as well. So I'm going to kind of show you. We also ran a test on the multiple zero crossing point, and I kind of want to show you what the waveforms look like. So at the end of the light load test, we actually save the data. And so if you look at the waveform screen, you can kind of see how distorted that is. So notice here's your voltage is a sine wave, but notice your current is way out. Another interesting point is this was a light load test. Ran a 1/4 amp. The question I had is, notice these 2 fields here. One is fundamental and one is RMS. Steve, can you explain to me why these 2 numbers would be different?
That's a really good question, Chris. Basically what's going on there is, what you're seeing there is that you're seeing the difference between the fundamental energy, fundamental once again being 60 hertz, and the total energy. The top number, the IFDRMS, is basically incorporating all of the harmonics, including both the fundamental harmonic plus the harmonic waveforms. And then the fundamental is only the 60 hertz component. And so for this particular example, we're measuring about 250 milliamps on the fundamental and about 320 milliamps on the total system. And so once again, that's a representation of the percentage of, there's a lot more harmonic energy. If we look down at the bottom, you actually notice the current THD is about 85%. And so there's a lot of harmonic energy being put into that. Once again, in the real world, the way that manifests itself is that harmonic energy is being burned up as heat. It's not actually doing useful work, and so it's going to overheat your transformers, it's going to overheat your equipment. It's bad news. The more harmonic energy you have, the more likely that heat's going to cause long-term damage and probably early failure of the equipment.
Steve's correct. It was interesting. You know, if I go back and look at these results, they look excellent.
Yeah.
Meter registration looks perfect. But Steve is exactly right. What's gonna break down is your transformers, especially. We've seen high harmonic distortions wear out transformers, tripling the neutral, wearing out the neutral phase. Eventually, if that neutral goes loose, it could cause a spark and a fire. Anything else to add? I think we've got to wrap it up.
Yeah, I think, once again, in summary, harmonics are still a problem, a lot of times more for the equipment. Good news is a lot of the more modern meters take care of harmonic energy, but do run your own test. And be aware, once again, if you can actually change your VA, if you're doing VA or VAR metering, be aware of how that's being calculated.
Thank you, guys. I appreciate you hanging with us. I know we went over a little bit. But those of you who have a 3 Series and 335, hopefully now this is a little bit of education that this option is available. And I hope you learn a little bit something about harmonics. Thanks for sticking around. We'll see you guys Thursday. See you then.